Okay, so after this sort of problem, I'm still happy that we have Stephan Mescher who will talk to us about topological complexity. So Stephan, let's try to aim to have a break at a quarter past 3 or something like this.
Okay.
We just move everything around.
Okay. Yeah. Thank you very much, Thomas. Thank you and thank you all the organizers for the invitation. It's a really nice opportunity to talk to different students. And now it's really after the strange beginning, but now I think it should work. So I can't see any one of you. So if everyone's falling asleep or something else is happening, just let me know. I'll just see the screen here. Okay, so I'm talking about topological complexity today. And oops, sorry. Okay, here we go. Okay. Yeah, I've called it Topological Complexity Introduction and Perspective, and so I've really divided the talks by two and into two different parts. So the first part, to just give you an overview, is supposed to give you an introduction to topological complexity and to all the basic things around this. I will do some examples. So first I will tell you basic properties, and then we will do some computations of some spaces which are really interesting from the point of view that occurs there. And then since it's related to robot motion planning, I will then talk a bit about collision-free motion planning. So about some particular aspect of topological complexity, which is quite intuitive and should be interesting for everyone. And then in the second talk, I've chosen to do it a bit differently. I will talk about 4 recent topics. So kind of current research. So I think the oldest of those is 3 years old, so it's very recent stuff. And so I will give you an introduction to 4 separate things, which are kind of mutually independent. And so just to give you an overview of the things, and I think there should be something in there for everyone. But I will start with the very basics. So yeah, let's do some motivation for this. So I'm studying the connections between topology and robot motion planning. And what do I mean when I say robot motion planning? So some situation that might occur in the real world or that occurs somewhere in robotics is that we have some robot which is moving in some warehouse or a grid network or some other workspace, but it's moving autonomously. It might be 3-dimensional or 2-dimensional on the ground or something, but it's supposed to move autonomously. And this means if the robot knows where it's at and where it's supposed to go to, it's supposed to find a way on its own. And this is the situation we want to formalize in a topological way, in an idealized setting, namely by interpreting the robot as a point in a space. And if you really want to formulate this motion planning problem in an abstract way, we arrive at this issue. So assume we have some path-connected topological space, some arbitrary space at first, which is the workspace of the robot modeling. And so if we view the robot as a point, this means that given 2 points, x and y, where x is supposed to be the start point or the point where the robot is at, its current location, and y is the point where it's supposed to go to, we should find a path in the path space. So px or py or something will always denote the path space, by which I mean this continuous path, so continuousness from the unit interval into the space, which start at x and end at y. So this is what the robot needs to do. And if we want to do motion planning in the whole warehouse, of course, we need some larger space. So this means for a big set of points, the robot is supposed to find its way on its own. And this is what we formalize in this way. We take, again, in topological space, we take a subset of x times x, so pairs of points. And a motion planner over this whole set A means that it's a map from A to the path space, such that with every pair of points, we associate such a path which starts at x, ends at y. And so this we want to do for all spaces in A. So to tell the robot how to move for all these pairs that occur there. So formally, this map, which has this property here, is then a section of a certain fibration. So if you don't know what fibration is, think of a fiber bundle or a generalized fiber bundle in some sense. We take the path space and map it to the pairs of points and evaluate it at beginning and end point. And so S is then a section of this map. So this is the way we get some topology to do with this. And of course, as the robot is supposed to move autonomously in the whole space, we need the motion planner over the whole product x times x. So for every pair of points, we need such a path. And to make this work in a nice way, we want a motion planner to be very simple. And by simple, I also mean that the robot should behave kind of predictably, and we should kind of in some sense, it should not be like if points are close together, the paths that the robot is choosing should also be close together to each other. So we don't want it to behave completely wild if we just have slight changes of position, just to have some like you might imagine if it's some interaction with humans or something, we would like the robot to behave in a predictable way and not do something chaotic. And so the question is kind of how can we do this? What can we achieve? And there is some bad news. This is something, a theorem by Michael Faber from 2003. Michael Faber is the guy who basically invented all this stuff and really started this field of topological complexity. So we have a continuous motion planner, which is of course the ideal version because it's really predictively so close. Yeah, close together means the paths are close together in a certain sense. And so there's a continuous motion planner over all of x times x if and only if the space is contractible. And this is something that you can easily see with a very simple example. Suppose the big rectangle here is the outside walls of some warehouse or something, or some workspace, and we have some obstacle here in the middle, say a shelf or whatever. And the robot is standing at point x, and it's supposed to move to different locations. Like if we wanted to move to y1, we would choose a path which would maybe look like this or similar. And if it's supposed to go to y2, it's also taking a path like this, so at some point. But as you can see, we get some problem as soon as we consider this point, y3, which is kind of on the opposite of the shelf here. So the question is now, do we go left, do we go right? But inevitably, at some point, there will be a jump. So we have to decide until which point or to which points we connect from the left and which we connect from the right. But this is inevitable. So you cannot avoid so you cannot get a continuous motion planner because of precisely this thing. So at some point, you have to make a decision of where to go, and then you will have a jump. So some points endpoints that are close together will have completely different paths. So to see this formally, I just want to prove the one direction. So if we have a continuous motion planner, then the space is contractible. That's the more interesting direction. And this is very easy to see, because if we have a continuous motion planner for all spaces here, we can define a homotopy by just saying for each point and time t, we take the path going from the fixed point x0 for some arbitrary point here. We just follow back the path we go from x0 to x, and this is then really easy to see that this is a contracting homotopy, because this contracts x completely onto this point x0. And so this is how we get a contraction. The other direction is also not too hard to see, but I just want to talk about this. But this is really what shows that this continuity doesn't happen. So this is, of course, bad news, because most spaces will not be contractible that occur because of obstacles or whatever. So the question is kind of what can we do now? So we want them to move predictively. So we want, and the idea is we want them to be continuous. It cannot be continuous on all x times x, but we want it to be continuous on large subsets of x times x. And we want these jumps that occur in the path assignments. So this, do we go left, do we go right or something? We want these to be, we want as few jumps as possible to make it as predictable as possible. And this is now the point where topological complexity comes in. Namely, the idea is we search for the lowest number of jumps that a motion planner is taking that is kind of determined, or that's necessary, just given by the topology of the space involved. And this is how we define topological complexity. That was also by Michael Faber from 2003. We take an arbitrary path-connected topological space. Then the topological complexity is a natural number or plus infinity. And this is just the smallest number n, such that we can cover the whole space x times x by n open subsets, such that over each of these subsets, we have a continuous motion planner. So just covering by relatively few, as few domains as possible, which have these this nice property of having these motion planners. So this is just the definition. And as you might guess already, this is quite hard to compute explicitly, but we will see some examples in the next slides. Before we do so, I just want to discuss some basic...
Stephan, can I have 1 sec? There are some people who have some more technical problems.
Okay, should I wait or?
Yeah, I don't know. Like, I just wanted to check how many people have technical problems, because if it's just 1 or 2 people, I would ask them to just rejoin maybe and use Google Chrome.
I think, Thomas, most people are wondering why we only see 3 lines. Yeah, so seemingly Stephan is already already continuing further with his talk, but kind of the slide seems to be frozen.
Oh, I'm on slide number 5.
Yeah, but there's only 3 lines on this slide.
Okay. Yeah, when this is okay, then it's good. Then it's good.
Sorry, 3 lines?
Yeah.
The only things we can see are we want robots up to have a few jumps in the path assignments.
Yeah,
that is the
so it
only
ends
thing we
with
can see on
path
this slide.
assignments.
Oh,
Yeah.
This is only the top third of the slide.
Oh, okay, right. So we need to rejoin then. If that is not supposed to happen. I think.
Okay, can the others see the whole slide?
I'll rejoin.
Can you change the slide for a second to try? Or will you stop maybe the share, Stephan, and stop the presentation? and do it again. I'm very sorry for all the technical difficulties.
No, not your fault. I mean, okay, let me.
And maybe Thomas, we could advise that everyone switches off his or her video, because that usually leads to better stability. I mean, at least with the Zoom meetings, that was our experience.
Okay, we can do that.
Yeah, so
Okay.
no one needs to see my unshaved face. So.
Okay.
Can you see slides again?
Yes.
Yes.
Yeah. Okay.
Right.
Oh, that's good. Yeah. Yes. Good.
Yeah.
Now we can see the full slide, and maybe Stephan, sorry, there was also a kind request from someone if you could speak a tad slower, because some people with bad connection they cannot, let's say, they can't that kind of stack on top of each other.
Okay, yeah, sorry, I try.
Thank you.
Okay, I can't see anything again, so just tell me when to continue.
You can start.
I can start, okay. So maybe if I'll just quickly go through the slide again, if you couldn't see it. So the idea is we want to search for the domains which cover the space x times x with the lowest number of possible jumps in these path assignments. And this is what this notion of topological complexity is encoding. We take the infimum of all n and n, such that we can cover x times x by n open subsets, such that over each of these subsets there exists some continuous motion planner, so a local section of this path vibration over each of these uj. So this is the number we can then define in this way. Of course, as you might already guess from seeing this number is usually extremely hard to compute. But I will discuss some techniques and some examples of how we can compute these things and how to decide about this. But first, I want to discuss some basic properties. So first of all, for concrete motion planning, there's a bit problem because these sets are, of course, overlapping. So on the overlapping parts, we technically have to decide if we really want to write a motion planning algorithm, which of these local sections should be taken. But the good thing is that this is not a big problem because we can also compute the TC in a similar way. Namely, if X is a Euclidean neighborhood retract. So if you don't know what this is, think just of a beautiful space. So some space that can be nicely embedded into R to the n. So for example, a compact manifold or finite CW complex. Then we can just do the same and say we can it's the lowest number n, such that we can decompose the whole space x times x into n disjoint mutually pairwise disjoint subsets, which are each locally compact. That's some technical condition that occurs there, and such that over each of these subsets there is a continuous motion planner. So this really then tells us how to really construct a motion planner on these domains here. Okay, some elementary topological properties, and this is now an interesting insight by Faber. TC of x is a homotopy invariant. So if we have homotopy equivalent spaces x and y, then they will have the same value of TC. So it only sees the homotopy type of the space. But this also is interesting from this motion planning point of view, because this says motion planning, kind of this complexity of motion planning only depends on the homotopy type. Then there is a nice upper bound for this, namely if we have X and R connected polyhedron. So a polyhedron in the sense of Spanier, I'm using this here, this kind of saying it's a triangulable space, basically, so a smooth manifold, for example. Then we have a nice upper bound. We can estimate it from above, TC of X by twice the dimension plus
Sorry,
R.
Stephan.
Yes?
I'm so sorry, but the slides is frozen again.
Oh, okay.
It's,
Okay, then maybe I'll stop sharing and try again.
If this happens too much, maybe. No, there's nothing. I mean, if this happens too much, maybe it's then useful to people to just download these slides and hope that they can fill it in a little bit.
Mm. Okay, can you see my slide again?
Yes. Yes.
yes.
Yes.
Yes.
Okay, so let me try. Let's do this then once per slide, and then okay. So we have this upper bound here. So if we have an R-connected polyhedron, then we have a dimension from above, which is first given by, an estimate from above, which is first given by the dimension, so twice dimension plus 1, and then divided by the connectivity. So the more connected a space is, the simpler motion planning is becoming this way. So we have this, we divide this by R plus 1, and then additionally plus 1. So this is a nice upper bound that we get for topological complexity, and that is useful to make good estimate in many situations. Okay, another remark, of course, just something very elementary. TC is 1 if and only if the space is contractible. This is because of the theorem I had before that you only have a continuous motion planner on the whole space when it's contractible. So this is just rephrasing this. So the value 1 cannot occur for any interesting space. Okay, I will do a first example of a first slight overview of how to compute these things. So what's the approach of how to study this? In general, so it's very hard to determine explicitly because, like, if we can write down motion planners, it's hard to tell if there are better ones with fewer domains or not. So the usual strategy to compute this is basically to find upper and lower bounds. So first one search for a good upper bound, and there are some methods for this. First of all, this bound that I just had on the previous slide with the dimensional connectivity. Or sometimes it's also it also helps to find an explicit open cover with these sets admitting motion planners. This is easier said than done, but there are situations in which you can really do this, because if we have such a situation, we can at most have k as the value of TC of x. Then we do the same with lower bounds for TC of x, and there are also some standard techniques, which I will talk about this later for a bit. First of all, you can use cohomology methods, so we'll quickly talk about this later on. And you could compare this to other vibrations, and whose value we can determine easier, or who we can study more easily. I will also give an example later. But usually the idea is kind of we try to find upper and lower bounds and want them to coincide. So this is usually how TC of x is determined. And this can be very difficult. I just want to give a quick example of this. Namely, there's one example which took very long, namely the Klein bottle. It was shown in 2016 by Dan Cohen and Lucille van den Broek that TC of the Klein bottle is 5. And this was open for 13 years, so I think people have tried this for a while, but this was really very complicated, and the proof is not exactly beautiful, so it's very technical. But this is you need some really advanced cohomology methods for these for this computation. So just to show you that this can be not that easy. Okay, so let's do the first example with one of our favorite kind of spaces, namely spheres. Simply, first of all, since spheres are non-contractible, we know that the TC of a sphere is 2 or bigger. So this is what we know. So what we now need is to decompose Sn times Sn into domains where we have these motion planning algorithms. And the first one is a very instructive one, because we take, as a first step, we just take all pairs of points which are non-antipodal to each other. So just all non-antipodal pairs of points, because then we know if we embed Sn as the round sphere inside of R to the n plus 1, we have a unique minimal geodesic between 2 points, so a minimal great circle segment from X to Y. Sorry, this picture is labeled a bit strangely because I've stolen this from Wikipedia. So here the points are P and Q, but to connect P and Q, I would just take this minimal great circle segment here, which connects the 2 points. And this, if I do this over all non-antipodal points, it's kind of a standard theorem from Riemannian geometry, maybe, that this is really continuous and this works nicely. But you can see the antipodal points, we cannot use this anymore, because if you here take the points U and V, which are antipodal in this picture, we already have several minimal geodesics. For example, 2 halves of some circle here, so each of the semicircles would be a minimal geodesic. Here we would have another great circle, and of course we would have an infinite family of great circles, which all give these things. So we need to make their choices of some semicircle, and it's easy to see that this cannot be done continuously. So we cannot just have a continuous extension of this map to all of Sn times Sn. So we need to treat the antipodal points differently. So we need to make choices of semicircles, and there is a nice little trick for this. And here we need to make a case distinction, because the odd and even dimensional cases are different. If we are in an odd dimensional sphere, we know that there exists a non-vanishing vector field on the sphere. And we can now use this vector field to give us the direction of the semicircle we should take. Namely, we take as the second domain here all pairs of antipodal points. And our section is then the parametrized semicircle, which is just changed into the vector field at the starting point X. And since the vector field is then chosen continuously and so on, this gives a continuous map. And this works out nicely. So this gives a second domain, and now we have covered everything. So we have shown that we can decompose Sn times Sn into 2 domains over which we have such sections. So we know that the topological complexity is bounded from above by 2, and together with the lower bound, this tells us the topological complexity of an odd-dimensional sphere is 2. In fact, it was even shown by Lupton, Grant, Oprea that they are the only spaces with topological complexity 2, but this is not that trivial. So let's take a look at the even-dimensional case. Here, of course, we don't have that's kind of standard theorem from algebraic topology that we don't have such a vector field. But what we can do is to find a vector field which vanishes at precisely 1 point, at the point x0. And what we then do is kind of to treat this 1 point separately. So what we first do is we take the pairs of antipodal points for all but this point x0, which we have to distinguish, and define S2 as before. So we can take these parameterized semicircles tangent to the vector field. And then we treat the remaining points separately. So we just take a third domain, just the set with 1 point, and we can just take an arbitrary semicircle. So it's, of course, nothing's happening. So these are continuous. So in this case, we can decompose Sn times Sn into 3 different domains. So we can at least tell that the TC of Sn in this case is at most 3. So together with the lower bound, we can now determine that this is either 2 or 3. And it will turn out that 3 is indeed the solution, but we have to increase our lower bounds and to get some additional technology, and I will come back to this in a few slides. Okay, so first of all, why study topological complexity? Because there are several aspects of why this is an interesting thing. First of all, there might be, and this is something that's really kind of, mathematicians and engineers are sometimes talking to each other, but unfortunately not too productively. To find practical applications to design automatic mechanical systems. So to really ask how good can our motion planning algorithms be, or how simple can we discuss them. This would be, of course, first of all, the task of collaboration between mathematicians and engineers. The second aspect is that there are connections of this TC to other problems from geometry, because as we will see later, if I have the time, this is we'll see how it turns out. The TC of real projective spaces is really does have to do with the existence of some immersions of RPN into Euclidean space. And this is some kind of classic immersion problem from topology, which is quite a classic issue, and they are really intimately connected, as we will maybe see. And third of all, it's just interesting in its own right, because it's a homotopy invariant. So we can of course ask, so what is this topological content and how does this behave? And there was one problem that was also supposed by Faber at some point. Namely, we can compute the topological complexity of Eilenberg-MacLane spaces of the form k pi 1, where pi is a discrete group. So spaces which have a fundamental group pi, but all other higher homotopy groups vanish. And we know for these spaces from topology that the homotopy type of this space only depends on the group itself. So the question is, how can we express this just as an invariant of pi? So without studying topology at all, just algebraically. And this is a really complicated problem, and I've also worked on this as well with Faber, but there are several class of examples where it's known, but the general answer is there's still not a good answer to this, but several really intricate technical approaches. Okay, if this looked familiar to some of you, I would just briefly mention another construction, namely the good old Düsseldorf-Schneermann category. When I use the word category in this talk, I'm not meaning this in the sense of category theory. It's just because this term existed before categories in the modern sense were invented. So please don't get distracted by this. When I talk about category, no categories are here involved, so don't be afraid. The Düsseldorf-Schneermann category is an invariant that is defined in a very similar way. Namely, we take the smallest number n and n, such that this time we can have an open cover of the space X, such that the inclusion of each of these open sets is null homotopic, so homotopic to a constant map. This, of course, looks quite similar, and we will see soon why how these two are connected. But this is some really classical invariant that was studied in topology for quite some time. I think it was in the 1920s or something when this was invented. And the motivation, just to give you a reminder, is the connection of this invariant to critical point theory. This is a kind of classic Düsseldorf-Schneermann theorem, which they had in 1934. So they had the finite dimensional version, and the version I'm stating here is by Palev from 1965. There are still more general versions, but anyway. So in case we have a Hilbert manifold M, and we have, so if you don't know what this is, just think of a finite dimensional manifold, that's fine for the moment. Then we take a function which is continuously differentiable and so of class C11, so its derivative is locally Lipschitz bounded. if this function is bounded from below and satisfies this Palais-Smale compactness condition with respect to some complete Finsler metric on the manifold, then we know that the number of critical points is bounded from below by the Lysenko-Schnirelmann category of M. So it gives a lower bound for all critical points of all function on the manifold which have these relatively nice properties. This is, of course, some of you might be familiar with the Morse inequalities. They give much stronger conditions on these numbers of critical points, but unfortunately you need the Morse condition for such function, which is not required here. So this is in that sense more general. And if you're interested in this Lysenko-Schnirelmann theory and everything that's involved, there's a very good book by Cornea, Lupton, Oprea, and Poiré from 2003, which basically contains everything you always wanted to know about Lysenko-Schnirelmann category from all kinds of different aspects. That's called Lysenko-Schnirelmann category, the book, so I strongly recommend it. So this is another invariant that looks similar, and it turns out that both of these invariants are special cases of some more general notion, which is called sectional category. This is from Albert Schwarz from 1961. And this is a general construction. Namely, in general, we take an arbitrary fibration between topological spaces from P from E to B. The sectional category, sometimes also called Schwarz genus of P, is then given by the smallest number, so denoted C-cat of P, the smallest number n, such that we can cover B by open subsets, such that over each of these open subsets, we have a local section, a continuous local section of our fibration here. So this is, again, this is a very general spirit, but the idea of definition is the same way, and it turns out that both Lysenko-Schnirelmann category and topological complexity arise in as sectional categories, namely, TC, basically almost had it because we already have seen this fibration. This is a sectional category of this path fibration, which just takes paths in X and evaluates them at beginning and end point. The Lysenko-Schnirelmann category is the sectional category of a slightly more simpler section because we just take paths which are based at some fixed points. So we just take a fixed starting point x0 and we just evaluate these points at the other end. So we just evaluate these paths at the other end. So this is, again, a fibration, and it really turns out, I won't prove this here, but that this is indeed the Lysenko-Schnirelmann category that comes out of this. And if we use properties of sectional category, we can also connect these two invariants in some sense. Namely, we can establish nice fundamental inequalities. We can see that TC lies between the category of X and the category of X times X. So it's in between these two, but in between these two, everything can happen. So there are basically many examples where you can see that you can construct examples where everything in between, all kinds of combinations can happen there. And there is one important case where both coincide, namely in the case of a topological group. Then we can really see that TC is always the Lysenko-Schnirelmann category of G. Okay,
Stephan,
yes?
Sorry, so was this known to Faber when he introduced this topological category, or is this later found out that it fell into this sectional category which was forgotten or something like this?
This was known to Faber. Yeah, he already realized this, so he saw this as a special case, yeah. Yeah, I don't know if it's already contained in the basic paper, so I mean, he at least mentions this paper here, but this was known to Faber, yeah. Okay, can I continue? Or?
Yes, I'm nodding, but I have my camera off, so that is super.
I can't see anything. I only see my slide. That's so okay. So this is a general construction for fibrations, and it turns out that we can kind of use. So Schwarz has it's a very long paper that contains all this stuff, but he has very general results for sectional categories, and we can then take them and implement them for topological complexity to get some nice results. And the interesting thing, first of all, one more example. There's one other example of sectional categories. I only want to give the definition, so-called higher topological complexities. So the idea is kind of, if we have this motion planning problem, and we have robots moving in the space X, we want to model the case that the robot needs to pick up stuff on its way. So it's not just going to its endpoint, but just passes some intermediate steps in between. So this is also something we can model by sectional category. Namely, this was done by Yuli Rodiak in 2010. The idea is now that we just do not take paths and evaluate them at their endpoints, but we just evaluate them at the times 1 over n-1 for 2 over n-1 and so on and so on. So we have these intermediate steps. And this map is again a fibration. And it's, the nth topological complexity, as it's called, is then defined as a sectional category of this pi n. So this is the same thing with kind of modeling intermediate stops. I don't want to talk further on these things, but this is how you see kind of how you can really use this sectional category notion to get some, it gives a lot of flexibility in that sense. Okay, so for sectional category, so this was studied by Schwarz, and Schwarz really gave some connections to homotopy theory. And so I would just, since I've already seen at least one homotopy theorist in the audience, I just want to give a very short overview about the main ideas that connect this to homotopy theory. Namely, there is first of all, I'll give a general construction. If we have two fibrations over the same space B, we can construct a so-called fiber-wise join of them. We'll do this with a star with an F as for fiber-wise. This means that it's again a fibration, and the fiber over a point B is then just given by the join of the fibers of the two fibrations here. So the topological join, that's the general construction here. So just over each fiber is the join of the two fibers we had before. And this construction gives again fibration, and this is so just a general abstract thing. And now we use this to give just if we start with one fibration, we just do a whole construction and we define a whole family of fibrations, Pn from En to B, by just taking the fiberwise join of P with itself and again and again and again. So the first of these fibrations is P itself, and the nth one is then the n-first one, and taking the fiberwise join with P. So we do it again, 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 and so we iterate this fiberwise join construction n times. So this we do for all n, and the question, of course, is why. And this is kind of maybe the fundamental theorem of Schwarz's work, that the sectional category is indeed the same as the smallest n in n, such that this fibration Pn has a global section, so that there is really a continuous global section over all of the space B. So now you might say, great, why do I do this? So now, before I had the local section of a simple fibration, now I have a global section, but a much more complicated fibration. But this is kind of a type of problem that is, it's kind of natural to study in terms of homotopy theory, like the existence of sections of fibration. This is some kind of bread and butter problem, I'd say. But the idea is now that we can kind of use methods from homotopy theory, for example, obstruction theory and so on. And so there's a lot of machinery that we can use now to study sectional category with methods from abstract topology and from homotopy theory. So this is kind of the key ingredient here to this study, which I will not go into detail much. But using this study, we get a lower bound for sectional category. Using this approach, we get a lower bound for sectional categories in terms of cohomology, which is what I want to give here at the moment. So assume we have some topological space Y, some commutative ring, and some ideal of the cohomology ring with R coefficients. Just as notation, CL of I denotes the cup length of I, which is defined as the biggest n, such that inside this ideal, and I take the only positive degree classes, so I intersect this with a reduced cohomology here. So I can find n cohomology classes in I of positive degree, whose product, so the product of all n classes with each other, is non-vanishing. So the nilpotency of the ideal, as an algebraist would say. So this is some general construction that appears in many places, also in critical point theory, I'd say. But here we have this has a very interesting point, namely if we take an arbitrary fibration and an arbitrary coefficient ring. In fact, you can only do this with local coefficients, but this is what I want to avoid today. You can show that the sectional category of P is bounded from below by the cup length of the kernel that we get with the pullback of the fibration. So this here as an ideal in the cohomology ring of B, this is just some ideal here, plus 1. So this gives us really a nice lower bound in terms of the cohomology ring. And this is something that's really, the cohomology ring is usually computable, and you can really do stuff with this, so you need to find out kind of only what this kernel here is. So this is the general construction. And now I want to see what comes out for topological complexity, because there it's even simpler. You can even formulate this a bit nicer. Namely, we study the following space. We take the kernel of the, so we again are in the product x times x, and we consider the product, the diagonal map that goes from x into the product x times x by just taking two copies of the same point here. And we take the kernel of the pullback with the diagonal. So everything that's vanishing here. And this I call ZR of x, and this is after Faber, I call this elements of this ideal I will call zero divisors. And now you might ask, okay, are they easy to find, these zero divisors, the kernel of the diagonal? And there's a nice construction method for these. Oh, I haven't, sorry, I thought I put this on this slide, it will come on the next. So it's not that hard to find zero divisors, as we shall see in a moment. So first of all, so this theorem by Schwarz, as a corollary, I'll formulate this was observed by Faber, shows then that TC is bounded from below by the cup length of the zero divisors here, plus 1. And this is something that's not too hard to prove, so I will briefly show you how to derive this. So we get directly from Schwarz's theorem that TC of x is bounded from below by the kernel of the pullback of this path vibration. Oh, here's a typo. This is, of course, an x. The pullback with pi from the cohomology of x times x to the path space. But we know the path space is homotopy equivalent to the space x itself. Namely, we can just take f as a map from x to px as the inclusion of constant paths. So with every x, we associate the constant path which maps everything to x. And then you can see that this diagram here commutes. Namely, if we take a constant path and evaluate it at its endpoints, is the same as just taking the diagonal from here. This is a very easy thing. But since we know that f is a homotopy equivalence, we know that in cohomology, this here gives an isomorphism. So this means that the kernel of this map in cohomology is the kernel of this map in cohomology. And this is precisely what's said here, because the kernel of this here is the set of zero divisors. So this is how this estimate arises. And yes, as I said, zero divisors, we can construct them, because if we start with an arbitrary cohomology class of x, we can just construct a zero divisor on x times x, of course, by just taking here the cohomology cross product with the class 1 as a zero-dimensional class, 1 times sigma minus sigma times 1. When we pull both of these classes back to x, we just end at sigma, and so we get sigma minus sigma, and this is 0. So this is a general construction method for zero divisors. Of course, when we take their products, we have to pay attention with the products and the signs of the cup product and so on, but this we will see in a bit. But this is a way how to obtain good lower bounds for this. Just something I want to mention, these bounds, the problem is that the cohomology ring might be interesting, but it also might be not interesting at all, because there are many situations when you can't get much information from the cohomology ring and the cup length is actually really low. But there's a nice technique of so-called category weights, and the idea is kind of that we can associate with every class in the reduced cohomology of x times x some natural number or 0, such that the number is 1 or bigger if and only if the class is a zero divisor. But it could just be much bigger. There are some techniques how you can compute these numbers, and yeah, it's not that easy, but sometimes it works. And the idea is now that if we then have classes whose product is non-vanishing, say we have k different classes whose cup product here is non-vanishing, the cup length lower bound would tell us that the TC is bigger than k plus 1. Is at least k plus 1, but this tells us now here we can use these weight techniques to bound it from below by the sum of the weights. And since the weight is 1 or bigger, this is k or bigger in that setting. So here we can really get much better lower bounds if we have good techniques here, and these weights have some nice algebraic properties, so that we can really sometimes use them to improve these bounds drastically. But this is something I don't want to talk about here because it would be a bit too much. Okay. So we had some unfinished business with the spheres. We had seen that the even-dimensional spheres have topological complexity 2 or 3, and this is now an example where this lower cohomology bound works. And now I can really demonstrate you how this works in action, because I want to show now that TC is 3, so we need to show that this cup length of the zero divisors is 2, because then we would get 2 plus 1 as lower bound, and this is what we need. So we do a very simple thing. We take the fundamental cohomology class of the sphere, just as a cohomology class in R or Q, it doesn't really matter. And then take the associated zero divisor that is constructed, as I indicated before, by saying 1 times the class minus the class times 1 as a zero divisor. And we can then see that the cup product of this class with itself, if we just compute this explicitly, then we get -2 times the fundamental class times fundamental class, which is non-vanishing, obviously. And so this means that the cup length is at least 2. You might wonder why this only works for even spheres. The problem is here that for odd spheres, that because of this graded commutativity rules of the cup product and the cross product here, we will get that this product would indeed vanish for odd dimensional spheres. Because so just the signs work out differently. So it's here we have kind of 2 classes with a sign of -1, which add up to -2. And for the odd dimensional situation, we would have a class one's positive and one's negative sign, so they would cancel each other out in this setting. So here we indeed get that the cup length of the zero divisors is at least 2. So this means by the previous corollary, the topological complexity is at least 3, and since we already know that it's at most 3, we can determine that the TC of the sphere is 3 if n is even. So this is really something we have confirmed now. Okay, I want to compute some more interesting examples, and I want to present to you some spaces that are interesting also from the robotics point of view. And I will start you with something very robotic, namely with a robot arm. We imagine a robot arm which is kind of moving planar. So it's not, we only have a two-dimensional situation. And we imagine that we have kind of some metal bars which are connected by joints, which is usually what we take as robot arms. And the idea is kind of to have this, like in this situation, I've no copyright on this picture, but at least I indicate where I stole it. This is stolen from Faber's paper, Topological Complexity of Motion Planning, which was kind of the first paper where he introduced this concept. So the idea is we have here these metal bars, and we have connected them by some joints, and they may, of course, rotate here. If we want to model the space of positions of this, so kind of motion planning for this robot arm, how it should behave. So for simplicity, we assume that these metal bars cannot collide, so that they are kind of on top of each other or something. But if we want to kind of describe the positions of this thing, of course, we don't need to describe the whole position in R2 of everything. We just need the angles that we have here. If we consider these as bars of fixed length, we only have these angles of rotation that are really interesting here. So in this point, we have 4 metal bars. And to describe the position of this robot arm, we only need the 4 angles that we have here at the beginning of the bar. So these are, so here 4 angular coordinates. And so if we want to describe the space of positions, this is just, if we have m different arms, this is just S1 to the m, which is also known as the m torus. So here the space is really the m torus that occurs here. And so for this space, we can also compute the topological complexity. And since this is a product of spaces, we need to decide what happens with the TC of a product. And there's a general thing. So if we have Euclidean neighborhood retracts, so nice spaces, then the TC of the product is bounded from above by the sum of the 2 TCs minus 1. So this is something I don't want to prove, but there's a very nice explicit proof for this. And if we do this iteratively with this m-fold product, we just arrive at this estimate. We get that the TC of the torus is smaller than or equal to m times the TC of the factor here S1 minus m minus 1. And we have already seen that this TC here is 2. So we got 2m minus m plus 1 here, which gives plus 1, m plus 1 as an upper bound. And then we can use the cohomology ring again. I don't want to go into detail about this, but the cohomology of the torus, we have kind of the generators of the m different factors. We can use their product and to get some m different zero divisors whose product is non-vanishing and get the lower bound here as well. So in this case, we can really see that the TC is m plus 1. So we need m plus 1 different domains to have this continuous motion planning for such a planar robot arm. We could do the same thing by allowing the same linkage to move 3-dimensionally. Then this means just for every arm, we need to fix a position in S2. So this is just kind of when everything can move in R3 freely. So this space of possible position would then give S2 to the power of m. Of course, now idealizing this by assuming that nothing can collide or something, so that the arm cannot kind of get knotted or whatever. So it will be just S2 to the power of m. And here you can use a similar method. Here you can show by the same way, using the same upper bound again, that it's bounded from above by 2m plus 1, because here we have a TC of an even dimensional sphere, which is 1 bigger in our computation. And we can again use cohomology methods to show that really TC of this space is indeed 2m plus 1. So this is what happens kind of when we increase dimension. Another very simple example that's interesting in robotics is grid networks. So assume we have some automatically guided vehicle, so let's say an automatic train, which is on some wire network. So some wires inside a warehouse or some rails or whatever, but inside some fixed network. If we want to study this topologically, we can of course say that this wire network is simply a finite graph. And the graph we can then see topologically as a one-dimensional CW complex. We don't need to talk about lengths or metrics or something at this point because we're just studying the topology. So we have this finite graph. And there we can also make a nice explicit computation. The TC is either 1, 2, or 3. 1 if we have a trivial fundamental group, 2 if the fundamental group is Z, and 3 in all other cases. And this is something that is really easy to prove because if we have a trivial fundamental group, we know from graph theory or something, so if there's no circle in the graph, it's contractible. So in the contractible setting, we have TC of the space is 1. In this situation, that the fundamental group is just Z, we can basically contract a lot of unnecessary edges and preserve the homotopy type and show that gamma then has the homotopy type of S1. And this is what we already have computed. Then the TC is 2. For the remaining case, if the fundamental group is not Z, but a bigger thing, then we get that this is kind of elementary theory of CW complexes, basically that the fundamental group of such a finite graph would be a free product of copies of Z. So this is the free product of groups for some number n at least 2. And we could see that the space itself, gamma, is then homotopic to a homotopy equivalent to a bouquet of circles. So n different circles just by contracting edges in some sense. So there you can then compute, this is also easy to see because the cohomology of these things is clear, or it's easy to determine, that the cup length of the cohomology here is 2 or bigger, and you can also then derive that the cup length of the zero divisors will be 2. So the TC has to be at least 3. But on the other hand, it's a one-dimensional CW complex, so this upper bound by dimension that we had, this gives us that TC is bounded from above by twice the dimension of the graph of the complex plus 1, which also gives 3. And so we have bounded from both sides by 3, so it's indeed equal to 3. So this is another thing that can be done quite easily. Okay, this is now we come to a situation which is kind of interesting also from the geometric perspective. Namely, we consider real projective spaces, and this is also something that's kind of natural in robotics in a certain sense. Let's assume we have some symmetric metal bar that that doesn't have a particular shape, so both ends are the same, and we have fixed it at some point in the center, and we just want to kind of distinguish how many positions are there, but we don't want to distinguish between the two ends. So we kind of consider the symmetry, and then it basically depends on the position of the line that kind of extends the bar in R3. So this means the space of positions could then be described as RP3. The three-dimensional projective space, lines in R3. And this leads then, of course, to the question, what is TC of the real projective space? Here we can see if we kind of use these upper and lower bounds, so the cohomology cup length bound and the upper bound by dimension and so on, this is not really helpful because this only tells us that TC of RPN is somewhere between n+1 and 2n+1, but there's a big range, of course, between these two. This was determined by Faber, Tabazhnikov, and Yuzvinsky in 2003, because they show that this is indeed related to a similar or to a different invariant from another problem, basically from differential topology. TC of RPN is either a certain number IN in these 3 exceptional cases here, or IN+1, where IN is just the smallest number k, such that we have an immersion of RPN into RK. So some immersion problem for real projective spaces, which has been studied for quite a while. I'm not too familiar with this, but you can really see that here really is a connection. I think for many ends, this explicit value is known. I think then Faber has some papers where he has some kind of small table of an overview of of the values that are known. But this is something that's kind of computable in many situations, at least until a certain dimension. I want to say a little bit on the proof, but I think I will skip the details there because I'm running then out of time. First of all, the one inequality to show that this is bounded from above, this can be really shown in a nice explicit way, since if we have an immersion from RPN to RK, we can use this immersion to really construct local motion planners with k different domains. This is kind of a nice computation, which I want to skip, but this is not too complicated. It's very direct, very explicit, which you can then do with the help of this immersion. The other direction, I only want to skip the big method of proof, like how can we see that this problem connects to this immersion problem? So the motion planning problem and the immersion problem, how they coincide. There's a nice little trick. Namely, we can, and this is what I meant when I said we get lower bounds by connections to other fibrations when we kind of want to study TC of X. Namely, the following trick. We take some arbitrary covering, a regular covering with covering group G, of the space X, so the covering space is X tilde. What we then do is kind of to take the product of the two coverings and quotient out the diagonal G action. So this is, we just quotient out this here. So we identify X1, X2 with GX1, GX2 for all G and all points here, X1, X2 in the space X tilde. And then get another induced map, which is again a covering. This is just a theory of covering spaces. This is again a G covering from this product here, X tilde times over G, X tilde to X times X. So this induces a covering. And then it turns out that TC of X is bounded from below by the sectional category of this covering. So this is, I will maybe skip the proof of this. But this is something that's also not too hard to see. And if we have such coverings, this means that for real projective spaces, we can take our favorite covering of real projective space. Namely, we always have a twofold covering of RPN by the n-sphere. This is, of course, just by identifying antipodal points. And we get, if we do this construction with this, so we take 2 copies of this covering, quotient out the diagonal Z2 action, and get the sectional category of this covering here. And this is the way that we can now construct connect this to this immersion problem in a nice way. Yeah, so this is basically, we can then, so this is the sectional category of this covering, and then we can use this result by Schwarz, that the sectional category is the smallest number, such there is a continuous section of this fiber-wise join, k-fold fiber-wise join of this thing with itself. And this looks pretty horrible, I admit, because of this kind of k-fold iterative thing of this covering. This is not really easy to determine, but it turns out that this is actually something we know, because if we take the tautological line bundle over RPN, so this is the line bundle which over each line associates just every vector lying in this line. This is the tautological line bundle. It turns out that this fiber-wise join here, this k-fold fiber-wise join for some k, is a unit sphere bundle of a bundle related to this tautological bundle. Namely, first we take the exterior tensor product of xi with itself, so as a bundle over RPN times RPN, and take the k-fold direct sum of this, which I denote by k times xi tensor xi. So this really, this gives, again, this is a vector bundle, and this then really gives the unit sphere bundle of this bundle here. This is, of course, highly non-trivial, so this to show this, but now we get to kind of the existence of a section of the unit sphere bundle. So this means TC of RPN is bounded from below by the smallest n, such that we have a section of the unit sphere bundle, and this can also be rephrased as the existence of a nowhere vanishing section of this bundle here, of this vector bundle k times xi times xi over this product of RPN with itself. So this number I want to call AN, and we can then use this AN to study and connect this to, maybe I'll skip through this. So there's a construction of so-called non-singular maps, and this is kind of the existence of maps from Rn plus 1 times Rn plus 1 to Rk plus 1 with some nice properties. And this is now the connection that we get to the immersion problem, because it turns out that there's a topological result by Adam, Gittler, and James. I don't know much about this from the 70s, but this number is then really, this existence of non-singular maps is really connected to the existence of immersions from RPN to Rk. And this is the connection how we can derive this. So we can show that this kind of is connected to the existence of immersions of RPN to Rk. Okay, just a small remark. This is kind of how we get the TC of real projective spaces. And there's this connection between TC and the immersion dimension also holds for length spaces. This was done by Jesus Gonzalez in 2005. But he basically also generalizes these methods by Faber, Tabashnikov, Yuzvinsky. So it's not an accident that it's there connected to this immersion dimension. Okay, since we have some symplectic people in the audience, by the way, can you still hear me?
Yes,
yes.
Yes, sure. You're fully audible.
We were just muted.
Yeah.
Wonderful. Okay, now I can, because I can see or hear anything. That's just checking. I just heard the horror story a while ago of someone who gave a Zoom talk and noticed after 45 minutes that his connection had crashed in minute 2. So just wanted to check. Okay, so for the symplectic people in the audience, I want to study symplectic manifolds for a moment, because in general, this is now, of course, not directly connected to motion planning, but the question is kind of how some nice classes of spaces behave with TC, and what does the TC tell us about these spaces. So let's take a closed symplectic manifold. So we have a closed non-degenerate 2 form on a closed manifold M, which is 2n dimensional, so even dimensional manifold. And the question is now, how can we attack the TC. So first of all, with the cohomology lower bound, we know here the cohomology ring has a big advantage, because we know if we have a closed manifold with a symplectic form, the cohomology form of this class, its highest possible product by degree, so it's n-fold product in this case, the cohomology class of this form. This would be, the highest product would be non-vanishing, because the omega to the n is a volume form, and so its cohomology class is the Ram cohomology is non-vanishing. And if we take the zero divisor that is associated with this cohomology class, this we write, so I'd call it sigma, and denote this by 1 times sigma minus sigma times 1. So with the classes, this is now a degree 2 cohomology class on the product n times m. It turns out that if we compute this basically with a binomial theorem, that the 2nth power of this is then indeed non-vanishing, because this gives then, it's just a straightforward computation, minus 1 to the n by 2n choose n. and then times the class to the n times class to the power of n. And since this class is non-vanishing, this is indeed non-vanishing. So we know that the zero divisor cup length is 2n or bigger. And so the topological complexity of the symplectic manifold has to be 2n plus 1 or bigger. So it's dimension plus 1 or bigger. There's a simple case when we really get equality here, namely when M is simply connected. If M is simply connected, we can use this upper bound I had in the beginning with dimensional connectivity. And it turns out that in this case, this boundary is like this. We have TC of n TC of m is bounded from above by 2 times the dimension plus 1. And now, since it's 1 connected, we can divide this by 2 and have to add plus 1. And this means that TC of m is smaller than or equal to 2n plus 3 over 2. And since it's an integer, it's at most 2n plus 1. So we get this upper bound. And since we have the same lower bound, we get equality. So in this case, we can really directly compute this without just basically follow some the ring structure here of the cohomology ring. The general case is a bit more intricate, and there's some result I want to present. So sorry?
This is, sorry, I have a question.
Yeah.
So can you go to the previous slide, maybe? Yeah, okay, thanks. So this is not really a symplectic statement, right? It's a property of this cohomology ring. Like,
exactly.
Or...
There is
okay.
a generalization. There's this notion of cohomologically symplectic spaces. This basically means that we have a space which has a cohomology class which behaves like this. Okay. And this works precisely the same way in this situation, yes.
Okay.
Straightforward generalization. Okay, so another case that I want to do some self-promotion here. If we have, again, a closed symplectic manifold of dimension 2n, there's a theorem by Mark Grant and myself from 2018, which has a nice criterion. Namely, it shows that if the pullback of this class, omega, to all 2 tori, by continuous maps, if all these pullbacks are vanishing, then the TC of m is 4n plus 1, so twice the dimension plus 1, which is kind of a dimensional upper bound that exists. So this is really a geometric condition here. So this we could call symplectically atoroidal, and this especially implies that it's symplectically spherical. But so this is some interesting condition that we found there, and the way this works. So I don't want to give you the proof, but the idea is kind of that this is a geometric condition which ensures that with these weights of cohomology classes I had before, then it really follows that the class of the zero divisor associated with the symplectic form has weight 2 or bigger. In fact, it's precisely 2, but this doesn't matter. But there we know it's really 2, and since we know that the power of this is non-vanishing, I said that's kind of then you can add up the weights, and since we have 2n, we take the 2nth power of this class, so this means that it's bounded from below by 2n times this weight, which is then 4n. And this already gives the upper bound. Since this really, this shows it's 4n, and so the TCM is, plus 1. Here's a plus 1 missing. I was just wondering, Here's a plus 1, and here's a plus 1, so we get this lower bound, and this is an equality follows from this dimensional upper bound. And so we have the simply connected case and this atoroidal case, but it's still an open problem what TCM is in general. So what is the TC of a symplectic manifold? Is there a way of determining this explicitly? And my personal guess is that this should be really related to the existence of symplectic torus actions, because this condition here, this atoroidal condition, this implies, as we found in our paper, that there's no symplectic circle action on the manifold. So this is the case where there's no symplectic circle action at all. In the simply connected case, we usually have torus actions. So this is kind of, in my opinion, it should be something it's really just a guess or a personal hunch that I have, that this should be related to this. And just as a nice indication, so how group actions can help here, there's a nice theorem by Mark Grant from 2012. If we have a closed manifold which has a non-trivial smooth torus action, TK action with a semi-free, so outside the fixed points it acts freely, then we have an upper bound of TC of x by twice the dimension plus 1 minus the rank of the torus here. So this really lowers this. And this is also something that's kind of intuitively clear, because if we think of motion planning, if a space has some symmetries, then we can kind of use symmetry to construct motion planners symmetrically. If we have them on some part, we can kind of use symmetries to translate this motion plan. So in fact, this existence of symmetries should simplify the motion planning problem. And this is kind of the interpretation of such a theorem.
Sorry, is this the same bound you got for like topological groups? Because then you get one for free, right? You have a compact sitting in your group, and then...
If for topological groups, you immediately get that TC of the group is the distribution Newman category. And this is usually just a lower bound for this. And yeah, this Differential category of symplectic manifold is also not completely known, but there are also some results on this. Okay. Yeah, so that's for symplectic manifolds. Then, okay, I'm already running a bit of time, but I'm just going to briefly talk about this collision-free motion planning problem. And this is also a nice thing that has some nice interpretations from this is where topology and this motion planning notions come together in a nice way. Namely, the idea is kind of that we don't want to just study the motion planning for one robot, but usually we have multiple robots working in the same space. So maybe they are kind of, I don't know, putting things from shelves back and forth or whatever, but we will have K robots moving in the same space. And we will kind of centrally control them all. So this would mean, first of all, that we would just have motion planning in X to the K. So this is just the general thing. So yeah, if we just want to formulate this a topological motion planning problem, this would mean just given K different starting points and K different endpoints, we want to find paths simultaneously, so gamma 1 to gamma K paths that connects the points xi with yi for each I, and so that we kind of have all these K robots connect, so that they are connected from the start points to the endpoints. But there's an additional requirement in practice, namely, we want that the robots should not collide. If these paths coincide at some point, we would have two robots crashing, and this is of course something we want to avoid. So we need to take this into account, that this doesn't happen. So if in this abstract problem we formulate this as an additional requirement, namely we want that all of these paths have the property that no two paths are at the same point at the same time. So gamma I and gamma j at t do not coincide if I and j are not equal. So this is what we additionally put on our requirement of our motion planners. This then leads to this so-called configuration spaces of X. And this is a natural notion from topology. And as we'll see on the next slide, this is really kicks in nicely. Namely, given some topological space X and some number K, which is at least 2, we just consider the so-called configuration space. So we take all, so it's an open subset of X to the K. We take all K triples of points in X, such that no two distinct points are the same. So this is just basically, we want that our motion planning takes place in this space, not in X to the K completely, but inside of this configuration space here, F of XK. So this is how we get collision-free motion planning. If we then want to plan this and want to have the TC notion, what we need to do is then to compute TC of this configuration space for just some suitable spaces X. But it turns out this is actually not that easy, because configuration spaces can be quite complicated. But there are some examples, and I want to kind of quickly go over them. Namely, the most basic example would be Euclidean space. And this has been shown, there are some, a part of this was shown by Faber, Juswinski in 2004, and then the general thing by Faber and Grant in 2009. Namely, if we have two numbers n and k and take the topological complexity of the configuration space of k objects in Rn, we get that the result is 2k minus 1 if n is odd and 2k minus 2 if n is even. So in particular, this really only depends on the parity of the dimension and not on the dimension itself. So this is really a nice thing to have. But the problem is, to study this, you really need some sophisticated techniques from algebraic topology. There's a lot of computations involved, like the cohomology of configuration spaces, how the cohomology ring behaves, and so on. This is so really abstract, and the problem is there was really no construction method for these motion planners. And of course, if we would really model this motion planning problem, this collision-free, which really has some practical applications, we would like motion planners. And so in the proofs of these things, we cannot just get them. And what I want to present now is just a very quick glance, since I'm running out of time, about motion planners in some case, namely in the case of R2. So in the case of R2 with k different robots, there's a construction by Hugo Mascou and Enrique Torres-Giese from 2015, who really constructed explicit motion planning algorithms in this case. Maybe let me see, time is already running out, so maybe I'll go to this very quickly. So the main idea is we take some...
Maybe we can also move it to the second part of the talk, or I don't know how long it will take.
I think that I've also got too much for the second part, but I just want to briefly say what I'm doing here, just very quickly. So the idea is I have some point in the configuration space. This means I have k different points in R2. And the idea is first I order them, because I first want to distinguish that I want to order them, first of all, by the y coordinate. And if some points are on the same y coordinate, I order them by the x coordinate here. So this means that we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So if we take some order, these points, the sequence of points would be ordered. And so for these ordered points, the idea is basically, let's skip this. Here's the picture. So we have some order tuple of points. We basically take a vertical line next to these points and connect all these points to the vertical line by a nice method that's kind of continuous in the coordinates of the points, so that they are all lined up here on this vertical line, just by their ordering. If we do this for two different points, which are ordered in this way, we have then two vertical lines with then points which have a nice ordering, and then can just directly connect the 2 points on the lines. So just connect the vertical lines with each other nicely, and because the ordering is correct, these lines won't intersect. And so we can kind of then basically go from one point to the vertical line, move to the other vertical line, then go back to the other point, and do this continuously. And this is for ordered points, and then we have to include permutations and so on and so on. So I will skip this. But it turned out that in this way, in the end, what you get is you really get 2K, you can get motion planners on sets with 2K minus 1 domain. They're not open sets, but 2K minus 1 sets. So this open is a mistake anyway. But you can, so explicitly complete continuous motion planners with 2K minus 1 different domains of continuity. And the theorem before said that this number, so this would then, of course, imply that the TC is bounded from above by 2K minus 1. But the theorem before said that this is the answer is indeed 2K minus 2. So we get motion planners explicitly, and there's a nice method for this, which is almost optimal, but not quite, but almost. And this was then generalized by Faber in some paper to arbitrary, so I think to odd-dimensional Euclidean spaces, but this method can be generalized. And so there are some construction methods for explicit motion planners, but this is really, in general, a very difficult task to construct them. So I want to finish by just saying there are some variations of topological complexity that I want to talk about, but just to give you an idea what you could also study at this point. The first notion is then by Faber and Grant, the so-called symmetric motion planning. The idea here is that first of all, we want to put some additional restrictions on these motion planners. They should behave reasonably. Namely, first of all, we want that if a robot is supposed to move from a point to itself, it just shouldn't do anything. We should have the constant path. This makes sense because why should it go in a circle or something? So this is just something that is reasonable. And we can put the additional requirement, this is also something that was not included so far, that if we go from X to Y, we should just take the same path as going from Y to X, but in the other direction. So this is also something which makes kind of intuitively perfect sense. But Faber and Grant then investigated what happens if we make these assumptions. What does change? How does the TC change? And there are some cases where you can study this nicely. Then another big field of study, which I won't go into today, is so-called equivariant topological complexities. And this is, of course, if a term equivariant pops up, we have spaces here with group actions. So we have some group action, and we want our motion planners to behave nicely, so to behave well with respect to some group actions. But the problem is that there are several different notions of these things, so the idea of equivariantness and so on. And as you can see from this list, there is kind of no canonical version. There are kind of currently 4 notions that I'm aware of that are in use. By various authors defined in the last years. My favorite is the last one here, this effective topological complexity. But it's kind of different purposes. So they have different properties for different purposes and different interpretations. So, but the message is just as you can do this. Then something recent I just want to mention is the so-called simplicial complexity by Jesus Gonzalez from 2018. What Gonzalez does is basically to define TC combinatorically for simplicial complexes. There in simplicial complexes, you have the kind of this discrete notion of the term homotopy called contiguity, and he's basically using contiguity classes and contiguity of maps to formalize this, or to have a combinatorial description of motion planning in simplicial complexes. This has then the advantage that you have, this is kind of combinatorics, you have algorithms there. So to really, how to construct motion planners which are kind of piecewise linear. So if you have a simplicial complex which behave linearly in each simplex, so roughly speaking. So this is some nice method of how you can really do some more algorithmic approach to this problem. Okay, so this is all I wanted to talk about in the first part. So to give you, in case you want an introduction, the best 2 sources if you want to know more things are just 2, one survey by Faber and the book by Faber. So the survey is just called Topology of Robot Motion Planning, and the book is a few years old, from Invitation to Topological Robotics. The book has the advantage that it's not talking only about TC, but to other aspects of topology and robotics as well. For example, there is in this, you can study configuration spaces of linkages, of mechanical linkages, and investigate their topology and their Betti numbers and so on. And so this is only part of kind of this, what is also commonly known as topological robotics. But these are kind of the sources you could start with. They are not on the recent, the recent things are not included there. As you can see, this appeared in 2006, but still it's the best starting point in my opinion. Okay, this is what I wanted to tell in part 1.